Raymond and Laurent, I don't know. I mean, if I try to introduce them, I think it'll be futile exercise. So maybe we can just go right ahead.
Okay, so this is going to be an interesting exercise. I've never had to share a presentation with Laurent.
Yeah.
And just put together extremely quickly this presentation. We're going to talk about our two different views, or well, let's say two complementary views on 6G prototyping, particularly related to SDRs, or software-defined radios. So I'm going to put actually a Eurocom hat on here because I'm talking about platforms. That's more Eurocom's baby, if you like. So we'll start with just a brief history of what we can call SDR history between Eurocom and OpenCells. Okay, that's a little bit how we got to know Laurent, which was quite a few years ago. And then I'll give the floor to Laurent to talk about some of the needs that he sees for 6G prototyping from the perspective of the business he's putting together. And then I'll put an OAI hat on and say, you know, what do we really need for OAI for 6G? From a community perspective here. So no licenses, no patents, nothing like that here. So before, just a little bit of history. I mean, actually at Eurocom, the activity that's been around, for those that were at the 10-year workshop last year, you saw my predecessor, Christian Bonnet, talk about our long history. We were actually an SDR house at Eurocom. But, you know, we were developing software, but we were actually also developing hardware. Around the same time as Edis was developing the first USRPs, we were actually developing things for our own little research community, primarily at Eurocom. And we had a variety of cards. And the last one that we built happened to have a name called Express MIMO 2. Should have been Express MIMO 4 because it was targeting 4G. It was a 4G card. Around that time when we put out that card, we got a call from Alcatel-Lucent. Alcatel-Lucent was a company that Eurocom has been trying to work with for so many years. It was the main French equipment vendor, and you know they typically worked with research centers and universities around them in Paris. They came to see us. That's when Laurent came with some of his colleagues and said, you know, we see what you're doing with OAI and the cards that you're building. Let's put it together with some core network software that we have in-house at Bell Labs, and see if we can't get it to interoperate with real UEs, and then it'd be interesting for us. And they were actually one of the first people that bought one of these SDRs from us. Okay, but around the same time, we had a visit from a good colleague from, at the time, Edis, almost National Instruments, saying, look, there are some people in China at Agilent that have written a driver for OAI so that you can connect our new USRP B210 with your software. Why don't you try and support that in the community? So we were a bit skeptical because we had this history of building SDRs ourselves, which we're very proud of. We had engineers in our team that were there for building the hardware, also writing software that works with it. OAI was, the first version was running on those cards. So we were a bit skeptical, but okay, we did it. There were people in the community, they were actually adding stuff. And so that was the end of our SDR manufacturing initiative at Eurocom, and we switched over completely to National Instruments. And that was the right thing to do because we could concentrate more on the software. And in fact, even Laurent's team at Alcatel, they switched completely over to the USRPs also. So we dropped that for a little while. But lo and behold, Laurent comes to me 2 years ago and he said, you know, I want to build another SDR and sell it. So
yes, but well, it is not yet for 6G for me. The SDR we show tomorrow is more for 5G.
And in some sense, he kind of took over from Express MIMO 2 because there's also a PCI Express for it, as you will see. And you know, so that's kind of funny, interesting. That's kind of funny from my perspective. So let me give the floor to Laurent, and he can explain certain things.
This talk is not about advertising our today's SDR. It is about what we need in 6G, because that's the difference with classical open source. We need hardware. We do radio. And so it's somehow a burden, but it's also what is unique. And today there is OpenAir, one competitor, but that's it, because it's very hard to do. We need that hardware. We need to do real things, not only software. So globally, we will need a higher sampling speed. So if we follow the track, it will be 4 times the 5G. We need more and more high band, and so we will need also new hardware for that. And I saw prototypes coming out for 5G, but it will continue. And we need low latency RxTX, and it's why I go back to PCI Express. But I think in 6G, we really need to find out low latency communication to the SDR that won't be Ethernet probably. And we need high spatial diversity because it is the largest trend. If you follow Cooper Law, Martin Cooper, that was the inventor of the cellular phone, and if you read that famous paper called Cooper Law, you will see that the highest gain over 1G, 2G, 3G, and so on is spatial diversity. It is not modulation, it is not even frequency, it is diversity. And we need also, and it's what Ethos has left now with NI and so on, we need open source hardware. And we need to go back to people that are able to implement FPGA firmware and to do open source hardware. So I took all the papers, so we see IA everywhere, so we need probably IA.
IA is French.
I see terahertz, so we will speak about terahertz. I see mid-bands. I see something, there is, in the 6G paper, there is a very impressive paper for me about vortex wave. And for me, it's something, nobody speaks about that, but in 6G it will be time to speak about even the wave itself. Today everybody is OFDM, IQ, and so on. But look that paper about vortex, and for me it's time to come back to modulation, to antennas, and to very basic things, not stay forever IQ and OFDM. That was 4G, 5G, but let's try to get out. We need energy efficiency. Yes, we see that already 5G, the beacons decreased a lot. And it's not only energy efficiency, it's we need to not pollute the space, because if we pollute all with pilots, then we have planned network, very organized, but it is macro cell and it's not the design for the future. The design for the future, you need to not emit energy except to transport really customer bits. And I saw a lot about new materials, supraconduction, but for me it's papers, and I don't think we will have that in 5G, in 6G. So 6G, I think it's quite clear. We will have to make SDR of 400 megahertz. On that, I wish if I do a future SDR for 6G, maybe I will not do even 400 megahertz. I will do just direct sampling, 0 to 6 gig. And I had prototypes a long while ago in Bell Labs with that. On doing just direct sampling is for me the evolution somehow. You see, before radio there was intermediate frequencies and so on. We remove intermediate frequency, but now at least 0 to 6G we can do direct sampling. Yes, about visible light, terahertz, and so on. So on that, for me, there is existing hardware. Nobody speaks about that, but my colleagues in Bell Labs, we are doing QPSK modulation, coherent decoding, and so on. at what they were calling optical, but their optical is about 100 terahertz. It's not that much. On all that electronic, if you want to use it, exists. You can do QPSK at 100 terahertz, and the modulated band is 25 gigahertz. On that modulator already exists. It is just what we call 100 gigabit per second Ethernet over the ocean and so on. And they have techniques. For example, when I was working with them, at least, it was not possible to lock the laser, so the local oscillator, really, as we do today in RF, we lock the receiver well, and so we have coherent modulation. They never managed to do that, so it was flickering. And so they were using, at that time, not IA, but maybe in IA now, after, they were just using a feedback loop with PID, loopback to compensate the fact that it is not possible to lock the local oscillator correctly. Okay, so that's it. No? Next, maybe? So yes, basic SDR that we have to do, I would say soon, if we want to do 6G prototype. It is 40 megahertz, 8 gigahertz in terms of modulated carrier, at least 4 antennas, but probably more. But it will be a huge data rate. Huh? For the mid-bands, I think we see it today in the demos, it will be up converters. Terahertz, so I said that if we take it from optical people, I think we have the hardware already, and we could make even very nice demonstration. Metamaterial, vortex, and so on. I don't think we will make it in 6G. And it's up to you. I mean.
Here, you want to?
I have, yeah.
There's more here.
Yeah, I have more slides, but well. Yeah, so yeah, I said it already. For me, PCI Express remained a good choice because in PCI Express you have low latency. I see, for example, in 6G requirement that they want to make 1 microsecond, so probably we won't make 1 microsecond. 5G is 1 millisecond. Huh? 5G is 2 slots, so it's 1 millisecond, at least at radio. You send the hack 1 millisecond after. In 6G, if you look at the requirement, they said 1 microsecond, but 1 microsecond is 300 meters of light speed. And it's not even possible to do that with packets. For example, in Ethernet switches, either you do store and forward, but then you have quite a large latency because you have to receive the packet before transmitting. Either you just forward on the first bits, on the header. But in radio, I don't think nobody will do that. So 1 microsecond, I don't think we will make it. Okay, next.
Okay. All right, so let me give maybe a complementary vision here. So what Laurent was expressing is right. I mean, it would be a generic PCI Express type board with fairly low latency. But that would miss certain things. Like for researchers that want to actually innovate in the fronthaul, that type of approach wouldn't have a fronthaul. So what I'm looking at here is a little bit more evolution, say, of the very high-end USRPs, which we're all using already today. I mean, if you look at the X410 and X440, to a certain extent, you could do some 6G prototyping with those already. You might not be able to make it all the way up in frequency, but the bandwidth, you would have it. For me, the main issue is that the channels are limited. Right? These are 4-channel devices, maybe 8 with the X440. Okay, it depends. If you're in TDD, it can be up to 8. And maximum frequency today of the underlying AMD components are 7 gigahertz, depending on the number of channels that you have. So, but that's today's technology. I mean, it seems reasonable to assume that it's going to improve in the fairly short term. But for me, what I really been looking for a very long time are community-driven platforms for 16, 32, 64 port devices. In Ian's presentation, it was 128 ports for 6G. For universities, I think it would be sufficient if we had a 64-port device to do work. But with 400 megahertz channels, and full FR3 band would be great, but 6 to 8 should be enough for most parts of the world. We saw that in the presentations today. For Europe, it's certainly enough. For the United States, it's certainly enough, at least for this kind of stuff. But 64 antenna ports for me would be something great. If we could come up with something as flexible as a USRP-based system with that many ports for real time, not just cascading USRPs in semi-real time, that would make sense. Of course, if we could get early access to early equivalent devices to ORUs to prototype the 6G fronthaul, that would be great. But that's not going to come immediately. So what we're kind of look at now is how would we develop in the spirit here of having a fronthaul type USRP, how would we develop a 6G equivalent of libxran? Right? That's a wonderful thing that the ORAN software community put out, that XRAN, because it allowed projects like OAI to connect to commercial ORUs. Now we can maybe innovate in that area too, take that as a base with an appropriate device and look at the fronthaul itself. All right, but I'm in the opinion here, at least from the perspective of OAI, we should still target Ethernet fronthaul and not go down below. But it's maybe a different use case from what Laurent was aiming at. I see a picture like this. Okay, so let's say our 6G DU, which would be a combination of CPU, GPU, look aside accelerators, connected to something. Maybe it's a smart NIC or a DPU. We heard a few comments about DPUs a little bit earlier. I'll give you the numbers in a second. I think you can do this with probably a 200 gigabit Ethernet link on the output. This is all technology that is perfectly feasible today. Maybe it'll be 400 gigabit and not 200, but it's something like that. Then obviously we need some form of matrix operations for beamforming, so there would be a front-end FPGA, and then a cascade of RF digital front ends. And these are an evolution of today's AMD or analog devices, silicon that exists. They have to go up a little bit higher in frequency, a very little bit. And then, of course, an array. So if we could build something like that for academic research, that would be very useful for innovating in the fronthaul, for innovating in waveforms for 6G. So this would be OAI's wish list, if you like, to the national instruments of the world to put something out like this. Okay. I don't know if it's going to happen because it requires the fronthaul. But if you look at some numbers with respect to what we're doing in OAI today with ORAN radio units, 9-bit block floating point compression, it could go up to 11 bits. It won't change very much. A 4T4R solution, 100 megahertz is 5 gigabit per second downlink, 2 gigabit per second uplink line rates. So that's easy on a 10 gigabit link. That's the way we usually do this. 6G 4T4R 400 megahertz is 20 gigabits downlink, 8 gigabits uplink. It's about half what Laurent said because he wasn't compressing and it was time domain. This is frequency domain. So if we go up now 16T16R, which is one of those RFDFEs, it's 80 gigabits per second downlink, 32 gigabits per second uplink. So this should fit with 200 gigabits per second Ethernet. Okay, so this is today's technology. We could do this. Now, what about libxran on a DPU device? We're looking at this now in the OAI community itself. Sticking the libxran, running it offloaded onto a Bluefield 3 DPU, which has 16 ARM Neoverse cores, well, 16 cores and 16 antennas. That fits very nicely. Not 16 antennas, 16 streams. It would do packet header processing, compression, and the 200 gigabit Ethernet. This basically also fits the requirements more or less. So current silicon for DPUs could fit that fronthaul unit that I mentioned. So that's why we're looking at this today in OAI for various solutions, how to put the fronthaul on a DPU. And similarly for beamforming and RFDFE, for me it's reasonable to assume that the current RFDFEs that you get from AMD or analog devices could be extended to 8 gigahertz and cover 400 megahertz channels. They already do cover 400 megahertz channels. Right, so I think, feasible almost on today's silicon. But we have to integrate that beamformer. That's the piece that is missing. So super USRPs like this would be great. Okay. So basically, we presented 2 views on SDR needs in a community. PCI Express, that's what Laurent's Open Sales is pushing. And I think from the Eurocom OAI perspective, we'd like to do more fronthaul. So it should have something that where we can develop the next generation fronthaul on top of the air interface and really be able to do massive MIMO experimentation. I think will be more relevant today if we do in 6G massive MIMO.
Thank you. Maybe one question?
In one of our slides, I think it was implied that you also consider some low functional split, like 7.2 or something.
I'm assuming that it's something like the 7.2, maybe also with the ULPI that Ericsson is pushing for ORAN type deployments. I would assume that. Yeah.
Okay, that would be helpful.
Maybe we could also innovate and look at different levels of split. That would be possible.
Yeah, and for me, I would like OpenAir do RU, so it's why I put the split below, because for me, OpenAir could target to do the upper part of the RU. That is not the RF board really, it's different technology.
Let's thank Laurent and Raymond. Okay. Yes, Jimmy, you have an announcement.
Yes. So, about studio visits, some of you have signed up. There's still room for more. We are running a little bit behind schedule. Actually, that's a good thing because it means people are talking and having a good time. So I'm not upset about that. But it means that we will, instead of doing the 1530 tour that's been moved to the 15 to 1530 tour has been moved to 1530 to 16. So if you signed up for that, just so that you're aware. I will also send these out into the audience so that everyone gets a chance to sign up while here. And unfortunately, that means we'll only have 3 slots for tours, but you know, first come, first serve. So there will unfortunately be no tours tomorrow. So this is maybe not a once in a lifetime opportunity, but
yeah. I highly recommend that. Yep. Last time I went there, it was great, you know, with all the Ericsson radio units and also use.
It's also where we keep some of the really fun stuff that we demo in Barcelona. So take the opportunity, not a once in a lifetime opportunity maybe, but at least a once during this event opportunity.
Okay, wonderful, thank you. Okay. Next speaker is Tim O'Shea. You know, I haven't known him very long, but he was very kind to have hosted me on one of my visits to his company, DeepSig. I think it's a very unique organization. It's sort of, for me, it's the new thinking in this sort of business, in this technology. So Tim is a faculty at Virginia Tech, but he's also the founder and CTO, co-founder and CTO of DeepSig, one of the companies that, as I said earlier, is very active at the AI RAN Alliance. So we really look forward to have your point of view about how 6G is going to pan out and, you know, the AI angle there. Looking forward to that. Thank you.
Thank you, Irfan, and thank you for having me here. So DeepSig was really, I think, born out of the software radio and open source community. Many of our early employees, including myself, were very focused on GNU radio and building out and prototyping different comms and sensing capabilities over the air using USRPs, using these great software radios and these great open source platforms like GNU Radio and OAI that have been huge enablers, I think. And so I think we feel a very close connection to this, but we've certainly also tried to balance our own business model to figure out what we can open source and what we have closed and how we strike that balance. So we're very interested as the whole 6G ecosystem evolves and considers openness and how much will be open to keep engaging as heavily as we can in this area. So, you know, our motivation really was looking at, you know, in 2012, 2013, obviously deep learning was exploding in computer vision. and looking at really transforming how you could do camera processing, voice processing, text processing, and none of that has slowed down. I mean, we just saw Google's new Gemini released yesterday that's like trillion parameter models that's just mind-blowing in its capabilities. And I still believe, as strongly as I did in 2016 when we started DeepSig, that this is going to be continue to be very transformative in all of the signal processing we're doing in wireless. And so thinking about this from the physical layer up, really the two key aspects, really ISAC, it's how do you communicate and how do you sense. These are kind of the two core functions in our RAN that we need to kind of master and use AI to continue to improve the efficiency of. And so starting to look at communications, there was a discussion earlier about, there's many years put into the current algorithms that are used widely today. In many cases, in certain assumptions, they're quite close to the Shannon bound. And so, can we push another 10x out of channel coding alone? Probably not. Can we push 10x out of any one of these? Probably not. But I think that when you look at the compounding gains of each different function within the signal processing chain of our wireless systems put together, there's a significant amount of capacity that machine learning can still bring to efficiency in our RAN and our radio systems. So what we're looking at here is basically, if you consider the ULPI split, which is starting to become really very prominent, I think, in the discussion around macro cell deployments, where you have kind of DMRS-based real-time beamforming in the uplink in your radio unit, and then you have kind of the standard push processing, either in your RU or your DU, depending on the split, or in a non-Open RAN system, of course. These are very much the same algorithms. And I think there's a lot of ways that you can leverage data and computational efficiency in each of these algorithms to improve 5G today. And then, as was said before, this really is the foundations of 6G, I think, is to figure it out, optimize it on the waveform today, and then figure out how to evolve and do something better and change more of the parameters than we have today in 5G to work with. So really the obvious big first one to look at that we've spent quite a bit of time looking at is the uplink push receiver in 5G systems. And so this is somewhere we started with open source stacks. We started with GNU Radio with some custom stuff, looked a little bit at OAI and some of the other open stacks that are huge enablers for this sort of work, and got some initial work going. And then we started to look at, how can we better test this in the real world, in macro cell deployments, where we can vet this out and get some real world measurement data for the impact that this could really have. And so this led us down the path of working kind of with Open RAN, because we could get into the DU, into the network components. And then working also with Intel FlexRAN, that's pretty widely used out there. And so this was an interesting opportunity to say, could we rip out some of the classical processing in the push receiver, put in a neural network, an inference algorithm, but then also figure out, how to optimize this to meet the latency deadlines. How can you run inference in 100 microseconds on a Xeon single core, right? These are difficult latency problems to solve. And so there's a lot of thinking that has to go into the neural network architecture and all of the techniques that can be used to try to make this very, very compact. So we've been doing kind of tests in this area for the past couple years. We were able to do some really cool over-the-air measurement work. We deployed in a trial in Viettel's macro network. We're doing these kind of end-to-end throughput tests in the uplink. We could see 2 to 3x throughput improvement, especially when you look at these edge conditions that are very low RSRP, which are really the problem spots in a lot of RAN deployments, often a pain point. So I think one of the things that's really important when we look at AI in 5G and in 6G is doing real-world measurement. I think this was mentioned earlier, but a lot of the statistical channel models really only go so far. Ray tracing is an amazing step on that, but we also really need to take this into the field and measure it in deployment situations wherever we can. And so somehow we need to close this gap between research and field test so that we know we're testing things that work in the world. So to that end, I guess we've also been looking quite a bit at generative channel modeling. So how do you take a whole bunch of measurement data? We've been doing kind of these drive campaigns with software radios, looking at passive reference signal transmission and trying to take all of this sounding data back from a network and go back and either calibrate a ray tracing model or calibrate a generative model or calibrate something in between that leverages bits of ray tracing and bits of machine learning. And then use this to emulate different channel conditions much more accurately. And this is obviously critical for testing realism and also for training. So your machine learning models, to perform well, they need to be trained on the right distribution of data. And so this is a critical function. And I think this plays directly into what will be a RAN digital twin to be able to try to capture these data distributions that you need in your network. What's the benefit of this? So, this has been kind of an evolving research thread in the field, looking at these site-specific machine learning models. And this was one figure from a paper we put at IEEE RAN a year ago, looking at, what is the benefit, in this case, looking at a standard MMSE receiver with a generally trained neural receiver for a wide range of channel conditions as compared to a neural receiver that's trained only for that site and that channel distribution. And so this is showing you, a couple dB step between each of those cases, which really highlights, we want to try to quantify, like, do we need to train these models locally or do we not? Because you don't want to if you don't have to. It's a lot of work to do all the data collection, but there is real benefit. And so, this is why we need to do these RAN digital twins. This is why we need this site-specific data collection, just to push more out of the algorithms. And you can also get away with much smaller algorithms when you do this, which allows you to improve the computational efficiency, the energy efficiency, the latency, and all of these things. So beyond that, think further down that compounding chain of gains. Take a look at beamforming. So when you look at ULPI, now you have some algorithm that's going to run in your RU, take all of this uplink DMRS data, and try to come up with the best beamforming algorithm it can. And so we've started to look at, can you do this using kind of a neural approach rather than the MMSE or ZF or the weighted MMSE or different types of beamforming algorithms. And have shown some promising results looking at kind of maximizing the sum rate for multiple users. And so I think if you start stacking these layers, each one may give you, some percentage gain in capacity. Taken all together, there could be really a significant capacity benefit to doing this. And this is another case where, we looked at Intel previously. This is looking at kind of ASIC type platforms. We've looked heavily at GPUs. I think one of the things we're seeing is all of these silicon platforms are converging towards having some kind of a tensor processor or a vector processor that can handle these sorts of workloads really, really well and efficiently. And this is going into kind of every sort of edge chip at a very quick rate, largely to support other applications, but a huge enabler for RAN as well. So then, what could we build if we didn't have to stick to 5G? So we started to look at, what if we weren't constrained to the existing standard? We know that we have pilot overhead today. We have kind of non-optimal constellation design. We have a lot of assumptions due to convenience in the way that we've standardized 5G today. And so if we try to relax those and pose this as an autoencoder problem where we're jointly learning basically the transmitter modulation reference signal design, the equalization and receiver algorithm, and the decoding algorithm as this jointly learned end-to-end process, you can actually kind of just allow standard machine learning models to learn this as long as you pose the question right through a accurate simulator of the channel. You come up with an architecture that can represent this learning very efficiently, and then you can watch it start to just kind of emergently learn new modulations. In this case, a pilot-free type modulation, so you can in some cases improve your capacity and reduce your overhead, at the same time. So, what could this look like? Really, we've tried to look at, how could this fit into the 5G OFDM NR slot structure that we're all very familiar with, and looking at, could this just replace certain key functions in the transmit and receive side without giving up a lot of the things like error correction, the PDCP and MAC, and all of the things that stack on it? Can we just slot this into specific functions to make this kind of as simple as possible a way? And so this is something we're very, very interested in, and we're doing a lot of work for non-standard waveforms in this area, where this can really help with resilience when you have different types of jamming or nonlinearity or degradation in your signal, to allow this sort of waveform to adapt around it. Right, so we've done quite a bit of prototyping, using USRP and NVIDIA type platforms. These are just some kind of chamber measurements looking at this. I'm very excited to see kind of the tools to make this possible continue to become much more available recently. And then just looking at benefits. So you can kind of compare and start to see the performance gaps when you compare this with traditional methods. You kind of get the sensitivity curve that you would see from a neural receiver, but without the overhead of the pilots. And so you can see it almost tracks the curve of the neural receiver, but then when you consider the actual data encoded in that amount of spectrum, your throughput curve is higher, right? So there's a lot of analysis to look at this, and I think this is kind of an interesting study item in the future. But it's really interesting to watch these things kind of emergently come up with new ways to communicate that work essentially just as well or better as what we're using today. And we can start to look at things like the semantic communications that's being shown over there, where we're not just encoding bits, but we're encoding different types of data. So you can see here we're basically learning a pilot-free, non-standard 64 QAM over the link here. Right, so I'll skip that. And then the last piece here really is about, the diversity in spectrum is increasing. I think we saw on slides earlier that a huge portion of 6G might rely on refarmed spectrum. And refarmed spectrum is always complicated because there's existing users. It's going to become maybe less dedicated in the future. And so we think similarly to some of the thoughts earlier that sensing in the RAN is critical for being able to work around different emitters, even for EMI and operations, but also for coordination between networks and within the network to make sure we're pushing the most out of the full spatial reuse of the spectrum. And so OmniSig has been kind of what we've been focused on, using a pattern recognition approach to understanding what activity is in the spectrum and labeling it in very short, like single-digit microsecond type timeframes, so that machines can make use of this in the scheduler, make use of it in the frequency coordination, and make use of it for diagnostic and O&M. So I think this is kind of a critical enabler for those sorts of applications. And on top of that, there's a huge amount of information. So for 6G, there's a lot of discussion about ISAC being potentially a new major revenue stream. And I think this is really true. But I think that passive sensing of activity around the network is almost equally as important as these kind of active radar type sensing activities, because both of those have a very rich amount of data about what is in and around your RAN, and how do we correlate that to what's going on in the physical world, continually build and update this RAN digital twin all around us about what is around us, what are the reflectors, what does the channel occupancy look like, what are the activities and trends of things in the RAN's area. And so digesting all of this information, in this case, pulling out several different LoRa bursts on different networks with different protocol types, and then associating them with like a spatial direction or location on a burst-by-burst basis is really something that wasn't feasible across a wide range of technologies, but is now becoming almost trivial just because of the abundance of edge compute. And so I think this is a really exciting area where as we look at ISAC and just sensing, this is something that can be in every radio unit at some point. And so we're starting to work with radio unit vendors to try to embed this into the RU function so that this can just be a service on top of the RAN as well. So thank you, I'll stop there.
Thank you. Any questions for Tim? So yeah, I wanted to ask you, how's this looking in 6G standardization right now? What's the feeling there? I mean, in terms of how the air interface, some of these new waveforms will look like.
Yeah, I think that there's not a lot of decision yet, right? There's discussion now around what will the release 20 study items look like. That's certainly a topic of discussion in the Malta meetings this week, and will certainly be a topic for the June Prague meetings that are coming up. And I think there's a lot of interest in being aggressive in terms of how can we leverage AI native to improve network efficiency and performance. But there's also kind of a hesitancy to do something that's going to wildly change radio units or hardware requirements. And so I think that's why we've been trying to focus on, is there a way to fit this into current structure such that this could be interoperable? You could have a joint 4G, 5G, 6G waveform with just different slot resource allocations. And so, I think those discussions are starting to happen. And, it'll be interesting to see, how aggressive will everybody be in terms of considering the broadness of the study topics. My understanding for 5G is that they were quite broad in terms of studying a wide range of new modulations. But, we'll have to see how that goes for 6G.
Florian? After Florian.
Thank you. So I have a question to the uplink performance improvement. So I didn't quite understand the neural receiver that you presented can be applied to the uplink PI as well, because then I mean part of the receiver runs in the radio unit already, and I don't think you can use any of your receiver in the radio unit, or can you?
You can. I mean, it's an algorithm, so you can load it on either one. The question.
But you need additional compute in there.
Well, right. So the question is, what is the compute, and can it handle the workload? Is it a workload increase or decrease? In some cases, it depends on the ULPI platform. I think there are, for instance, in the Intel case, we've shown neural receiver algorithms that are on the same order of magnitude of complexity as kind of a baseline MMSC Wiener filter. And so these can be shrunk down significantly. In some cases, you can use these really low precision wide operations that you might have to otherwise use floating point. And so there's some trade-offs, and I think some platforms will definitely be able to support this in the RU. I mean, we're starting to work on that as well. I think it's going to have to in the future if ULPI is continuing to be adopted.
Okay, thanks.
There's a question here from Luhan, and then the gentleman.
Okay, thank you, Tim. I'm Luhan from BUPT from Beijing. I'm very interested in the AI-based modulation and demodulation, as we also did some very similar work. You saw we have a demo there. So my question is that you did the AI-based modulation. Is it from beta level, like you?
That's right.
Yeah. The first question. Second question is that are you still need to do a channel estimation? Because in our settings, we still need to do channel estimation. Otherwise, when the channel environment changes, the neural network doesn't work at all.
Yeah.
Okay. Thank you. Thank you.
Yeah, exactly. So in that work, we were looking at encoding, like a push allocation block of bits. So you're still operating on bits. You're not going to this semantic content level, which I think could have further benefits for sure. But we do definitely need to worry about the receiver. And so we're jointly learning kind of encoding, decoding, and that receiver portion. And the nice thing is that
But if you change the environment, so how do you learn that channel?
well, so it's the same problem as a neural receiver. You know, you have to train it for any type of channel environment.
That's
that you
challenging.
Right, so you need to train against a wide variety of channel distributions and effects and conditions so that you have a model that generalizes well. And then you need to really rigorously test that under a huge number of different possible deployment conditions. And so that's been a lot of our work, is really how do you take these models and harden them so when I go to the field, it doesn't fail. Like, it works on every channel I can present it with. And that's really a hugely important part of turning any one of these AI approaches into something that can be reliably deployed, is hardening that training and testing process. And you can follow either this general approach where you want it to generalize very well to any type of channel, or this specialization approach where if it's in this one sector and it's only going to see these sorts of cell geometries, now I can start to specialize for that. But you kind of have to do, one of those strategies.
Yes, yes. Very interesting. Thank you.
Okay, we have one last question.
I have two questions. One of them is,
Could you please introduce yourself?
my name is Ammar Al-Falou. I'm working in King Abdullah University of Science and Technology in Saudi Arabia. Mainly, I have two questions. The first one is more related to your work. So, do you think that we don't need any more the theoretical part of research and move completely to AI?
No, I wouldn't say that. I think the theory is still super important. I think we need to assume more realistic assumptions in our work. I think one of the drawbacks of a lot of theoretical research is it has to look at, to keep it tractably handleable, you have to look at simplified forms of the problem. But I think one of the things that machine learning is really, really good at is dealing with very high dimension problem optimization. And that's the reality that we have in almost every wireless system, is we actually have, very specific sets of distributions throughout the system. And so the theory is always going to be critically important. But there's some things we can model in closed form and some that we can't. And so I think you want to take the best of both, learn from theory in the way you do the optimization, the architectures, the analysis of the problem, but then use machine learning when you really need to worry about these high degree of freedom problems that can benefit from real data sets and measurement. And so we're going to need both. I mean, the fields are kind of like crashing towards each other. And I don't think you'll ever escape both of them at this point.
The other one is not scientific at all. Did you get benefit from the name of your company because it's very similar to DeepSeek or?
We have had customers email us for support for DeepSeek. We had.
You can get some rewards on the stocks because
we haven't looked into whether they're close enough to our U.S. trademark, but.
No. I think Tim is an honest man. He wouldn't want to do that. Tim, thanks a lot. Thanks for your talk. It was great to have you here. It was a great talk. Thank you very much. Okay, so our last speaker before the panel is Maximilian Stark. Okay, there you are. We haven't met before. So he's with NXP Semiconductors, and the title of his talk is The Role of Edge AI in Smart Software-Defined Radio Modems. So
exactly. Yeah, so thank you very much for having me and having us. I think it's the first time that we are also here attending the workshops from the OpenAirInterface community and listening to all the nice presentations that we had before. I also know that, and I think I mentioned that in one of the questions I had, that there's a lot of focus on going towards more bandwidth, more antennas, bringing more AI into base stations, into core network, and so on. And I think it's a very important part. But to get a little bit a better understanding where we come from, I'm from the research department, so we are also involved in many projects with universities on European and national and international level. And NXP traditionally engages a lot in microcontrollers. So we are involved in most of the robotics, drones, for healthcare, industrial, and many other applications. And if you remember, when this 5G journey started, there was a lot of focus on what they called the verticals. So bringing new companies, new streams into this 3GPP regime. Yeah? So, and that we talked about smart farming, industrial 4.0, and so on and so forth. And in one of our projects, we noted actually that it's actually not so easy to find modems that you want to put in a drone that give you a full open source platform so that universities can play with the physical layer and the L2, but it's a form factor that you can put in a drone and you have full access to IQ samples, you have full control over the RF, and it basically comes with standard components that are already around and affordable, but they can be glued together so that they basically fit here on a drone like we were doing in a water rescue project. And the goal was to have a red cap 5G device running. And that's also when we know that actually there's a lot of support on G-Node B side and having a lot of support for cool features in the G-Node B. But when it comes to customers asking for basically if they can test a red cap functionality or some functionality that they want to put in the car or in a bike or in some devices that are really power oriented, there's quite some dependencies on if there's already a large enough market for chipset vendors to basically engage on. So we already saw that technically there's this tendency to go also in the third dimension, right? So this 3D networks, meaning that we all know our terrestrial networks, but then of course there were like first study items. I remember that when we started working on it in 3GPP, asking what happens if we have UAVs, so basically some drones flying around where our IMX family is typically inside. Then there were people starting talking about balloons or basically these high altitude hubs or aircraft. And this is also now what we see continuing in 6G. And then basically, of course, everybody is talking now about NTN, which is already quite far in the 5G discussion, but I think you also saw that earlier today when we talked about the first 3GPP outcomes of the 6G studies. There is somehow a convergence already at that stage that focus will be on NTN topics from day one, and of course AI. So, and the talk basically will focus on how we bridge things together and why I believe that also smart modems will be an important cornerstone to that one. So the first thing basically we did was this LAMX family, so the ones that are basically in the satellites, they were already in the satellites today for broadband access. And the first question is, why do we actually talk about all this NTN stuff, right? Of course, one very classical example is enhancing coverage that really addresses all these vertical markets. So basically when you think about trucks going around, fleet management, asset tracking on chips, or if you basically have smart farming applications. It's interesting because all these applications are very nice. They also sound always very great. But what we basically saw in 5G, that if you have too many different use cases and too many different feature sets, that results kind of in a market fragmentation, so that for each market, the volume isn't big enough so that it really takes off. And the second thing is also, we come to that also in a minute, that if new stakeholders come to the 3GPP ecosystem, they need to learn about this life cycle and also this release cycles, because technically, of course, if you hear that the new release is about to come in 1.5 years and it brings you new features, and you know your truck will be in the field for 20 years or your ship will be around for, I don't know, 60 years, of course, then technically it would be maybe better to wait 1.5 years to get more features, but in the end you wait, but you don't deploy. And that's also something which we hope will be better than in a 6G world. Yeah? So, and that's basically the first part where this 3D networks make sense. The second thing is, of course, something which many people talk about, and I think we also have seen it in the slides earlier today. Classical applications for 3D networks are resilience, where you talk about cyber attacks or having a redundant link, especially in autonomous driving. That's something what people fairly often talk about, of course, in natural disasters where you have an outage of the classical terrestrial network. Yeah? And also here you could say, okay, it makes sense to either let some drones fly, some airplanes go into the air, or you have some satellites. So in general, enhancing coverage, enhancing resilience. These are the main drivers to extend from already starting in 5G, but to 6G, going into this into the space, actually. But that leads, as I said, to some interesting questions. When you look at the 3GPP life cycle as it's today, typically it's 1.5 years, 2 years. Then you have new features standardized. It's very difficult to test them already in the early stage, especially on the UE side. So, and then, as I said, a good question is that our drone customers ask us, okay, if we have now a 5G system in our drone or if at our airplane or a satellite, how can we easily upgrade something that's already flying around? And there, interestingly, we see that there is some interest in reconfigurable software-defined hardware that is flying around, that is maybe not as efficient as a nicely designed ASIC, which is really optimized on an energy per bit level, but it has the flexibility. Once it's somehow in space, you can easily get some software upgrades to basically make it ready for the next release. And that's also here the same thing when you have, like, now on the UE side, things deployed in ships, cars, trucks, and so on. They basically think also, when you think about all these discussions in the software-defined vehicle world, where also over-the-air updates are getting more and more state-of-the-art, and why not also keeping that for the radio side. So, in general, our learning from 6G was that dedicated chips for all the different 5G features and all the different markets were not designed. Mainly, always the argument was that the volume isn't big enough. So basically, there were so many cool features in 5G that really didn't make it into reality. And that's basically why we also thought, okay, we do have these platforms, this LX platform, the IMX platforms, which are basically already powerful ARM processors that could easily run a stack. And we decided to start working with the OpenAirInterface stack for our pre-6G work and discussions to basically check how we can test features very early in research projects, but also if people want to play and start playing with the hardware. So today, we also heard a lot about AI, right? So AI or no AI, that's basically the fundamental question nowadays in communication engineering, because I think we had that in the beginning, that for decades, people were always optimizing. And I think Tim already showed it also on the slides, that maybe it's not good to go by a block-wise approach, but maybe it would make more sense if you glue more components together and then see some elements. And so for us, it's actually important, as I also asked in the beginning, in 3GPP, there's a lot of discussion ongoing on something which is called model lifecycle management, which basically asks the question, how do you handle if a UE needs to run a dedicated AI algorithm? How do you do all the stuff with capability exchange, that a model can be really offloaded to the device, that it's capable of doing that? So in 3GPP, there's a lot of discussion also involving about the framework, when to update models, how to deploy models, and that also requires that somehow you need to have a UE that has some AI capabilities already, that you can start playing with and working with. And for those of you, I think once you start with AI algorithm development, you maybe take a GPU and then you get your TensorFlow or PyTorch running and you have your model and you see great gains. And then also, when we basically start working with it, we started with this very simple example here of this autoencoder, where you basically have the constellations that kind of manage to optimize themselves such that for each SNR, they are even closer to the channel capacity than we used to be before. And then our question was that our chip designers ask, what would happen if you quantize it down to 8-bit integer precision, because that's technically what this NPUs, this very low power NPUs that sit in, so the neural processing units that sit in the microcontrollers, these are really tiny algorithms, tiny architectures, and they basically need to have dedicated optimization of the AI algorithm, so meaning also quantization effects. And that's basically what we did, and you will basically see that already on the top. This is this SDR platform that we are from that we are basically talking about. It consists of an off-the-shelf IMX8M Plus processor. This processor already has an NPU on board. You can buy it actually everywhere around. It also has a very small GPU for some video rendering purposes. We connected it to our baseband signal processing chip, which is the LA9310. It only takes IQ samples in the time domain. We just use the DUC and the ADC, and then we basically glued some RF on it. And basically what we saw here is that even if we have this autoencoder in simulation, or if we run it on the SDR, even with this 8-bit quantization that was basically required to bring it on the NPU, you hardly lose something. And that was basically for us also very important, that we have that we basically have a software framework, so that algorithms that we develop, we bring it then into TensorFlow Lite models, modify it so that they basically run on our NPUs. And I think that's also something what we will hear tomorrow, how it's in OpenAirInterface, we will now get the chance to use AI algorithms on real hardware. So in general, our decision was that we don't really want to engage in the software part too much. As a silicon vendor, we see ourselves more as providing hardware platforms, but we really believe, and that's also an initiative that is basically brought up by some initiative in Germany, which is the 6G for All initiative, where basically the goal is to support the open source community. So, and how does it basically work? I already showed you kind of the form factor. It's already the form factor of that size, so that's the biggest brother that we have. And the cool thing is, it first of all starts with, if you feel that you are an RF engineer and you want to design your own RF module, you can come up with your own RF IC. The schematics are basically open source. You can just download them. You connect them. There is going to be then an SPI connector. That one goes down to the Vespa cores. The Vespa cores perform the DUC and ADC. And then we have this open source API, which allows you to access exactly basically the IQ samples. And then we have the IMX application processor, which runs the ARM branch of OAI. We have the AI accelerator nearby, and we have another hardware accelerator which is basically used for crypto. So you have like an accelerator for security algorithms and for graphic algorithms. And the cool thing here actually about this device is that the gray boxes, these are the ones that we basically are leaving for the open source community, so that you can come up with your own RF design. If you want to do something for FR3, you are free to do that. If you want to do something for a very low frequency, you are also free to do that. If you want to put multiple antennas and you want to try something, that's always up to you. So the only thing that we basically provide is some DSP capabilities, some lo-fi API, as I said, and then we really appreciate all the efforts that you are doing on the OpenAirInterface UE side as well, and we hope that basically there we can contribute also to the RedCap branch a bit. So in general, why do we say it's extremely cost efficient? So without RF modules, the SDR board is approximately, I'm not sure, it's like around like $250. So because the components itself, they are basically mass components, it's actually very, very easy. Then, as it's an ARM processor and it runs in Linux on it, you can install everything that you want to install. With sudo apt-get install, you can get yourself kind of ready. And then also the hardware-based flexibility, kind of giving you the chance to change the different RF modules, also would be an option for you to basically play around with different RF components. And I'm often asked also if the RF components can work in different frequency bands and so on. So that really depends then on the details, but in theory that's kind of possible. So we then moved on. As I said, our final goal was to bring it on a drone. So a form factor of 20 to 10 by 10 centimeters, it's a bit too big. So basically we all scaled it down. We scaled it down to a chip that has a form factor 4 by 4 centimeters. So I put this €2 coin. I know I'm not sure what would be an equivalent in Swedish crowns. I'm not sure. I'm not so good with the Swedish currency, but actually it's fairly small. And that one is then designed to work in band 78, so it kind of has a dedicated RFIC, but also, as I said, so schematics are typically open, and you can discuss if you want to change something here. We decided to go for a campus network frequency because that, of course, makes it fairly often easier to then communicate in dedicated bands. And again, also this guy has a small AI accelerator for very simple AI-based band signal processing. So so basically, as I said, we are here also today to present this idea of these software-defined radio platform to support these edge cases. Edge meaning here really on robots, on drones, so more focusing on the RedCap design, on the narrowband, on the IoT design, on the NTN design, so that you can also test algorithms maybe that you are envisioning in your project, so that you can maybe put OpenAirInterface also into an end-to-end system so that you could have the full chain also, even if there are not mass market chipsets on the UE side around for your drones and for your robots. As I said, we will also continue to contribute to OpenAirInterface to basically provide this platform, RF design, and all the other stuff is open source. We have a open source community already working on the software enablement and keeping care of all this SDR API. Yeah, and in the end, of course, we are always open if somebody of you also would like to engage in getting the hands-on on the platform and work together in some research projects. We are also often of course, very often. Yeah, we are very here. So this is kind of the get in touch slide. So Hilke, she's taking care of the project management of this Europe-funded project. Wim is taking care if you really want to get into buying stuff, and if you want to get something done with OAI, you can always reach out to me, and the board you can already get today on rfnm.com. So that's kind of the platform provider and the crowdfunding source for that one. So thank you very much for your attention. So yeah, that's the acknowledgement slide to the European government and the European Union. Okay, thank you.
Thank you, Max. Thanks very much. This was a great presentation.
Thank you.
Any questions here? Anita?
Hi, Anita from Eridan. Nice to meet you. You said you are putting these things on drones, so I'm guessing you are also designing for a low power consumption on those. Can you give me numbers?
So yeah, so technically, so basically, the point is we do have. I cannot give you watts numbers because actually the IMX is the general processor that's running also all the motor management and so on. So basically we're just hopping on top, but basically you can easily power it with a classical USB-C for a 5-volt device, and I think it's in the order of 5 watts or so on of the entire chip. So that's.
Thank you.
Any other questions?
It's UE, yeah. So I mean, so the point is we always say it's a UE because we are afraid that people are putting too many PRB configurations on the device and then it's blowing up. So, but you can try to make it a G.B. You can buy it if you kind of either reach out to me directly or if you go to the website RFNM and then Davide will take care.
And if I understood correctly, it costs only €2.
€2,
Oh,
exactly. Exactly, yeah. So that's a very good question. So technically, it depends on which stack you want to put on it. So basically, this orange box here just knows about IQ samples. And if your IQ samples come from a 5G base station and you put a 5G stack processing this IQ samples, then it's a 5G UE.
She knows how to skid.
Okay, there you go.
on that board, yeah, it's RFIC from Metanoia working at N78. But we can talk. So basically, yeah, that's like you have antenna ports on the back, so it really sends some radio waves out.
Okay, let's thank Max again.
Yes. Thank you.
Very nice talk.
While
We have another announcement.
Yep. So while we get the panel up here, if we could switch over to my info slide and get that on screen.
Nice.
So they tell you consistency in your messaging is key. So that's why I'm going to give you a completely new message on the Ericsson Studio thing. So just in order for everyone to be able to attend, because we got a lot of people that wanted to attend tomorrow instead, we have a tour tomorrow. So if you signed up for group 2 or 3 or couldn't sign up, there's a tour for you tomorrow at 1500 to 1545. We also extended the tours because I talked to the guys in the studio and they're like, we have way too much cool shit to show, so we need to extend the tour by 15 minutes. We can't do that in half an hour. So group 1 that were supposed to be at 1500, 1530, we will now do the tour at 1530 to 1615, and group 4 will be 1615 to 1700. And we'll meet at the coffee station 5 minutes before the tour starts, and I'll take us down there. The studio runs a tight ship. I don't, so I will try to not make them disappointed with us by being late.
Okay.
Thank you. That's all, and we can get back to our regular scheduled programming with the panel.
Oh, I have this. So if if the panel keeps on going and you have the tour booked, feel free to move out. Don't wait for the panel to finish. But nevertheless, I'll try to keep it on time. So I invite all the panelists to the stage here. There's Raymond, there's Doug, there's Tommaso, Sebastian, and Ahmad. Oh, no. Sorry. You may take a seat. All right. While you get settled here, I believe there are microphones. I'm not sure there's a microphone for everyone, so you have to pass those around. Oh, if you want to sit in order, take this order.
I have. Wait.
All right, so you're swapping a bit. Okay, so the topic of the panel is the role of open source for 6G radio and core networks. So let me first introduce the panelists, and then I'll go through some questions, and each one of them has a few minutes to present, and then we will take questions from the audience. Some of those panelists have already been introduced, so I can be brief on them. Professor Raymond Knopp from Eurocom, who's also the president of OpenAirInterface Software Alliance. We have Doug Nicely from Qualcomm, senior director of standards, and he's also an OSI board member. And he's going to give a talk tomorrow, so he will take away probably some of the messages from tomorrow. Tommaso Melodio, you've already seen him today. He gave a talk today, professor at Northeastern, director for the Institute for Wireless Internet of Things, always a board member. And I forgot to mention here on the slide, he's also a founder of Z-Touch, which he mentioned in his presentation. Arnaud Mourad from InterDigital, senior director, head of Wireless Lab Europe, and managing director UK. And InterDigital is also on one of the strategic members of OAI. And then we have Sebastian Camara, who is a research scientist at NVIDIA. So welcome everyone to the panel. So the theme of the panel is the role of open source in 6G. So we already heard a little bit of history from Raymond today in OAI. So I joined OAI almost 18 years ago. And I joined at the time when we started to develop 4G. So with 4G, we were a little bit late, late behind the standard. So it took us, after the standard was finalized, it took us a few years. Raymond was telling the story of Alcatel-Lucent reaching out and collaborating with us on the core network. But eventually we got the 4G stack running, and it was a big success. With 5G, we were a little bit earlier. We had the momentum, and we delivered the 5G stack just I don't know how later we were, but a year or maybe two, just a little bit late. And so, but the vision of OAI has always been, to be the reference implementation for 3GPP, and with the vision was always Raymond's vision and my vision to develop the code in parallel to the standard. So now with 6G getting developed, I want to, the questions that I like to ask the panel is, how can we achieve this? How do we really make sure that with 6G we have, as the standard matures, we also have more or less the code developing at the same time? Yeah, what are the obstacles? How to overcome them? How can we work with partner associations? Yeah, so OAI has a lot of collaborations with 3GPP, ORAN, the AI-RAN Alliance. So how can we partition the work, distribute the work, so that we achieve this goal? And what should we really focus on? I mean, 3GPP, 5G is a very large project, and we heard that probably only 10% of it actually gets implemented. So we need to focus. So, what should we focus on? What kind of use cases, requirements, and technologies shall we focus on in OpenAirInterface? All right, so I'd like to, so I have some people sent me slides. Let's start with Raymond. And maybe you give your vision on how we can achieve those goals here.
Okay, I didn't prepare any slides, so I'm gonna wing this. Unfortunately, I will have to talk 2 seconds here about to answer this now, because of what you just said here about the patents and the license. Actually, I think it's a given. We heard it in Jimmy's talk this morning. The 6G ecosystem is not going to change. 3GPP is on its way here. Florian was saying that we really wanted to do this now in parallel with the standard. What that means now is some of our labs, if it's a Eurocom or a Fraunhofer or a university, a KTH here in Stockholm, if we really want to go and do that, which means go and participate in 3GPP, the open source becomes essentially in French it was la vitrine, or it would be your showcase of what you're actually doing. I mean, if you're a little research center, I mean, I won't say Fraunhofer because they're actually quite good at this, but a little research center in 3GPP has like zero voice. When we were doing this in really 17 and 18 in 3GPP, we were more learning about these things, and we weren't putting anything that we were trying into OAI. But now, if we want to do what Florian just said there with 6G, we actually want, as a small institute, to go and put things into 3GPP. We have to be protected, and this is the only way it's going to happen. If we go and do this in the open source community, we'll get very good papers. We might even get thousands and tens of thousands of citations, and our university will be super happy. But if you go and tell your director, well, actually, you just lost out at 1 million euros a year for the next 20 years, he's not going to be so happy. Okay, so that for me is why this has to happen. If we want to do what you just said, at 4G we were too late. There was nothing we could have done to impact the standard. We put out software, and it was there for people to experiment and maybe think about new things for later. For 5G, we were also too late. The implementations came out around the same time as the deployed networks, where companies like Ericsson and Nokia already had all of this 4 or 5 years ahead of time, and also all of the intellectual property and everything else. So I mean that for me is the way to make it happen, is to continue what we're doing right now, from a perspective of a small research center or university. And the open source itself is the way to showcase what you're doing and make the other people aware of what your innovations are, and then cut a deal with one of them so that you can get your share.
Okay. Thank you, Raymond. Let's go in the order you're sitting. So Alain, you want to... Ah, wait, you sent me a slide, right?
I think I sent you a slide.
Okay, I need to...
All right, okay. Yeah, so when Florian, you put that question to us in that email thread on what's the role of open source in 6G, I thought I would share some thoughts with you, starting with what we know about 6G, because we don't know that much, honestly, about 6G. But what we know for sure is the IMT 2030 that 6G is aiming at, enabling the user scenarios. So that's why I decided to start with that famous wheel diagram that I think most of you should be familiar with. And what's really interesting actually to note from this wheel diagram is, the usage scenarios in IMT 2030 compared to IMT 2020, they are doubling. So in IMT 2020, we only had that triangle in the middle, right? The EMBB, the MMTC, the URLNC. And actually what we are doing in the IMT 2030 is, expanding upon the IMT 2020 3 scenarios and adding 3 additional ones, right? And the 3 additional ones are the integrated sensing and comm, integrated AI and communication, and then ubiquitous connectivity. So that multiplication of the user scenarios, I think inevitably will lead to multiplication of features and complexity in the system, which actually, in a way, a great motivation for us to continue the drive for open source. Open source is, to me, it's a twin, in a way, from motivation standpoint for the complexity and the number of, multiplied features, in a way. So that's the first, thought I would like to share with you. The second is, if I were just actually to focus on what I call the relatively new user scenarios, so integrated sensing and comm and integrated AI and comm. So the nature of these 2 scenarios, they are less hardware, I would say, apart maybe from the radar sensing component for the ISAC, and they are more actually software and data, and more data actually. So my expectation is, as we move towards 6G, there's going to be more emphasis, especially on data, to support these scenarios. So basically having what we call end-to-end data and AI frameworks will be prerequisites, especially on the underlying connectivity fabric that, for example, OAI typically provides. So when I say, data and AI framework, what do I mean by that? So I mean, especially for the data, so way to measure the data, way to collect that data that has been measured, way to process, pre-process, post-process the data, way actually to analyze that data, way to expose the data, whether it is for services or it is actually expose it back into the network. So that's what I refer to as actually the data framework. And similarly, we have to put in place AI framework around, the model, the data training for that model, the inference, framework. So all the, the lifecycle management, as we know, it already happening in the 3GPP. So that's the AI framework that we will also need to put in place, as I call it, as a prerequisite for the 6G open source platform. Next, still in that same topic of data and AI, so we need actually also to pay attention to the governance and interoperability of the data and the AI. Right. So by governance, especially, I refer to considerations for security, privacy, trustworthiness. Right. So these are key, especially when you think about sensing. Right. For example, but it's not only limited to sensing. So we need to pay attention to that, and then sharing data sets for training, for doing inference in a distributed way and things like that. So you will also have to pay attention to interoperability of the data as well. Right. So we need to pay attention to these as well in the framework of the open source. And then, interesting enough, actually, when you look at that wheel diagram, there is this nice, call it wheel or circle, surrounding the 6 user scenarios. People typically don't pay much attention to these, okay? Sustainability, ubiquitous intelligence, and so on. But basically, there are aspects of these that I think 6G will need to pay attention to. So the 2 favorite topics I have in mind here, if you drill down from the sustainability, I think the aspect of energy efficiency, right? So I think compared to IMT 2020, where energy efficiency was, on the wish list, but it wasn't really on the requirements of the IMT 2020. In IMT 2030, it is expected to change, right? So we will need to make sure that there are ways to account for that energy efficiency into the IMT 2030 or the 6G, if you like. But also, when it comes to, the privacy, the resilience, and the security. So these things, cannot be just, if you like, looked at in a secondary way. So we'll have to bake them from the outset when we look at the open source platform. And last but not least, obviously the ecosystem, I think, is expanding. around the open source because the system is actually getting a little bit more, encompassing. So not only for I think we heard this morning from Tommaso around also the compute, the edge, right? So there are multiple dimensions that are coming together, right? So which making actually the ecosystem expanding in terms of stakeholders that are playing into that ecosystem. So obviously we need to make sure that there is no duplication, there is coordination, and there is alignment, not only on the technology side, but also on the licensing, matters as we discussed vividly in the previous sessions. And I elected to kind of share with you just recent publications or announcements. I think somebody made mention of this already on that US DoD launch of that open source software for 5G, 6G last month. But being also a big, ETSI fan, myself being on the ETSI board and also chair of the ETSI ISAC Industrial Specification Group. So I have to also make a call out for ETSI, which actually launched early this month, this new SDG software development group on open source operated platform, with the main mission actually for this, OpenOP, project, really to, target the 6G testbed federation based on the GSMA requirements. So hopefully this gives you some thoughts that are in line with the scope of this panel.
All right. Thank you, Alain. So let's pass directly to Tommaso. So I'll go back to the questions.
Well, yes, I was going to make 3 points here that have already been made eloquently by Raymond and Alain in different ways. So I'll just summarize them briefly. Point number one is, and this is something I say all the time, I think it's a great time for academic researchers to be in wireless. It's probably the best time ever. We have an opportunity to test concepts that are not only fundamental concepts in nature, but also very applied research, test it with end-to-end implementations of systems, demonstrate it, and get directly with proof of concepts to the decision makers and to those that are going to make these technologies happen. And this is something that has not happened ever before. And I think so it's very important for OAI to be right on time, ahead of time in the evolution towards 6G, because this is going to make an impact. So that was my point number one. And part of point number one is, of course, we need software, but we also need test beds that are going to be available to the community and to the academic community to experiment with. There's a number of such test beds, both in the United States, within the POWER program, and in Europe, within a number of European programs. One is licensed RI, and it's very important. It's crucial at this time. I think that governments continue to support these efforts so that we have these combinations between hardware and software systems that enable innovation in this space. My point number two is that, I think the title of the panel is role of open source in RAN and core. We need to go beyond RAN and core.
Okay. Yes.
I'm not scolding Florian.
No, it's...
No, but I think this is a point that has been made also by Alain, right? It's really an ecosystem that's going to include the ability to experiment with inference and sensing. We talked about it quite extensively with RAN intelligent controllers, with the AI and all the data frameworks that are necessary for that. So we need to continue to go in that direction. I think OAI has been doing very well in that space, in coordinating with a number of entities. And my point number three here is that I think there is an opportunity for OAI to become really the center of an ecosystem that includes the ORAN Alliance and the AI RAN Alliance in innovating in the space of convergence between intelligence, inference, and radio access network and communication. And I think, obviously OAI is very well aligned with the ORAN Alliance, with the RICS, and with all the infrastructure has been specified by the ORAN Alliance, and hopefully in the future will converge with 3GPP. And I think there is an opportunity also with the AI RAN Alliance in giving a little more structure to the efforts that are happening within the AI RAN Alliance in terms of integrating AI with the RAN and coexistence between AI and the RAN, and with all the software frameworks are going to be necessary for that. Over.
Thank you, Tommaso. Sebastian?
Yeah, I think
yes, you sent me a slide, yes.
Yeah. Essentially, I have one picture that I would like to share. It comes from ChatGPT, so I asked about the research reality gap and got this nice illustration here. So I think I could have even removed the bullet points here. So the point I want to make is, as I see myself as an industrial researcher and kind of trying to bridge the gap between, let's say, industry and academia. And I don't want to say that the one side or the other side does a bad job. It's just that I see that there is a certain gap between both worlds. And I think where OAI and open source software in general can actually help is that it can help to close this gap or to bridge essentially these two worlds. And that's something where I see talking about the panel here about how we can drive 6G and how we can drive innovation. I think that's something where open source can really help. Now, let me explain a bit just an example about that. There are many papers about neural networks for channel estimation, and there are, I don't know, 100 or 1,000 papers about that. But when you look at from the academic world now, when you look at the industry and you look at the DMRS and how it works in 5G, these pilots are rotating all the time. So they change within a sub-milliseconds regime. They on a per slot basis, actually. So if you have a network that is overfitted to specific pilots, it will actually never work in practice, except if you would replace your weights on a sub-millisecond time frame, which is actually not very practical. So I think there's really not a common understanding of how 5G works, what is the actual problem you need to solve, and what academia is currently doing. So that's something where I see open source as a tool to simplify this and to help actually also academia to understand how the standard actually works and take complexity from the standard. I mean, it's also impossible that each university re-implements the whole stack and does 5G compliant experiments. That will simply not scale. So that's the one point I wanted to make. And then it's not just about running the 5G stack, it's also about having the possibility to doing experiments. And I think what we are missing is at the moment that we don't have the good channel models, or that we have the channel models to drive innovation. It's a bit aligned with what you said before. So I think we need let's say more advanced channel models, more advanced test environments. You cannot run your 5G stack in a static lab environment. Typically, you want to test what happens under mobility scenarios, high-speed scenarios, what happens if you have multiple users, if you have interference and all these things. And it's very challenging to reproduce that in a lab environment. And I think there, digital twins really make sense to do a rapid prototyping of your algorithms, at least on a first stage, to validate that your research is actually that makes sense for practice. And then the last point is, of course, when you talk about AI RAN, about AI algorithms in the physical layer and the RAN in general, we need data sets. And what I've seen in the past is that there is not just the one data set or the one problem formulation like in other fields of machine learning, where you have a common benchmark and then everyone comes up with a better solution and you have one score and you can just compare that. I think we have a huge amount of small scattered problems, and each problem needs its own data set. And I think that's why I think open source is so important, because we do not provide the data set, but we provide the source code actually to generate data sets. So in OAI, I can actually dump a data set at any stage in the 5G stack in principle, and I get access to it, and I can create my own data set that fits exactly to the type of problem that I want to solve, or the type of learning problem that I want to tackle. And I think that's a very important thing, and I think that's something where we can help to drive 6G innovation. And I think with that, I hand over.
Thanks, Sebastian. Yes, and note that you're going to give a talk tomorrow exactly about the Siona research kit, right?
Yeah, exactly. So I'm one of the, maybe just 2 sentences, I'm one of the core developers of this Siona link level simulators. It's an open source project. It's to prototype, it started as a link level simulator. It now has system level capabilities and also ray tracer for RF propagation. It's all open source. We are not competing with OpenAirInterface. I think Siona is simulation, it's for machine learning, it's for rapid prototyping, and then the idea is that you can use the OAI stack to really deploy and test your models. And you can also collect data, of course, for training. So that's why I'm also having the points here. So we have these digital twins, these RF simulators as open source, and I think bridging this actually to the OAI code base, to the RF simulator, extending that would be something where I see a lot of common interest, essentially.
All right. Thank you. All right, Doug, how can we make a OpenAirInterface dereference implementation?
My slides say. The answer on it. I should have stuck with the ChatGPT generated diagrams to make things more interesting. Unfortunately, my slides are immensely boring. It's difficult to say anything after all of these because I agree with all the points that have been raised here. I guess the only thing that my spin would be is I think OAI has now grown up to be a kind of a boisterous teenager in the world with lots of enthusiasm and energy and has produced really amazing results. But now the pressures of the world to reach out and work with industry standards organizations, SDOs, 3GPP, ORAN, AI-RAN Alliance, as well as dozens of open source projects with different kinds of relationships and important aspects that need to be integrated with the OAI. I think OAI is at a cornerstone where it needs to either kind of stay where it is as kind of a very small contained project to support academic research projects, or it needs to grow up big time. I don't think we have a choice. I think we have to grow up. And so that means really expanding the scope of outreach and engagement. This is an organizational issue. It's a staffing issue. It's a integration and testing issue for sure. And it's also an architecture issue. The technical work that has to occur with all of these organizations to be, as you said, ahead of the curve for the first time in an unprecedented way in our industry, really, where open source and academia is able to be back at the forefront of 6G technology. Actually, we are ahead of the curve. People are using OAI to do 6G research literally before 3GPP has started the study items. Yes. They're just starting in the next couple of weeks in 3GPP just being kicked off. And OAI platforms are already being conceived and developed and integrated into research platforms for organizations studying 6G problems. The challenges are how do we scale, how do we grow financially, organizationally, architecture-wise, while still making sure that we have a good core team that continues to drive the architecture, keep it unified and consistent, as has been done, I mean, through so much effort and out of Raymond and you and others in the OAI team for so many years. But also maintains and builds the essential very sophisticated radio integration capabilities that need to be done, which is kind of the OAI core mission, you know, as opposed to developing the new features and functionality and so forth that goes into the stack. And that probably will not be able to be done by one team at one location. So that itself will probably have to scale and incorporate relationships with other integration. And by integration, that's really, it's much more than integration. It's actually RF expertise that is doing integration of sophisticated components and debugging the sophisticated components to make sure that they fit together and run together, and then tying that in with the where the research primary interests are. I think the bigger picture is how do we transition into AI, ML based orchestration and automation of the network. And so, and all of the digital twin technologies, you know, Siona being the most prominent example of those technologies in open source form. But we expect those to grow to be incorporated with full-scale automation platforms that implement all of the ORAN management architecture and the emerging 6G, 3GPP management architecture incorporated with that, both in the stack for at-scale testing, you know, end-to-end testing, which is kind of all of the core OAI stack, but with all of the automation built around it, and then correlated through digital twinning with the pure simulation ray tracing type environment to calibrate those. So important. So I think we need to figure out financially, organizationally, how to grow the organization and the scope of the work that's being tackled. And it's so important to the industry around the world, but we have to figure out how to make it happen.
All right, thanks, Doug. Thanks for all your answers. These were some great directions. I have plenty of more questions, but I'd like to also open the floor, maybe first to the audience. If you have any particular questions to the panel, I mean, in the context of our. Oh yes, we have one extra mic here. Anyone? Yes, that's okay. Sorry, he was first.
Thank you. My question is...
Sorry, can you state your name? And
I always forget that part. My name is João from the Wireless Intelligence Lab in Arizona State University. I work a lot with ray tracing data sets and reproducibility. And a problem that Sebastian mentioned in that bridge between academia and industry is, I think it has to do with benchmarking. And when I compare the AI community in wireless with AI in computer sciences, they have more clearly defined problems, and they have data sets that they use to essentially benchmark their solutions. It's a much more mature community for sure, but they seem to be building on top of each other more than we are in wireless. And I wanted to know if you think we should standardize AI problems with clear inputs and outputs, and then perhaps create data sets to benchmark those problems, or if you see any other ways of going about this reproducibility challenge and have more works built on top of each other.
Okay, that's a great question about the data sets. Maybe Sebastian, you can take a.
Yeah, then maybe I can go ahead. So I mean, there have been a couple of these typically competitions from different organizations, and I think there were also a couple of very interesting results coming out of that. My impression is that the field of wireless communications is so huge, and there are so many different flavors of it, essentially, that it is very challenging to define this, let's say, set of 10 most important problems. And it's also, we've also heard that today. I mean, it's a very complicated ecosystem where you need to understand your, I don't know, power amplifier. You need to understand what's the impact on up to the core network, essentially. And that makes it, I think, very challenging to come up with a set of, I don't know, 10 challenges. And that was one of the points I wanted to make, that as it's so complicated to have these challenges, the data sets, I think one way of going ahead is to come up with more realistic channel models and scenarios where you can test your algorithms, think about joint sensing and communications. The models that we have the 3GPP models are clearly not the right models for working on joint sensing and communications. And that's something where I think where OAI could actually take the lead essentially and define these channel models where you can then test at least under the same channel models or the same conditions, essentially, where you can compare your algorithms. That would be one thing I have in mind. But yeah, I'm just.
You want to
add something? Maybe I can add a little bit. I think compared to the computer vision, the problems that we face in wireless, right, and in wireless communications and in wireless networks are probably one order of magnitude of complexity, at least higher. And even just going into defining what are these 10 important problems to address, or whatever the number is, right? That's already a way to sort of categorize in a somewhat artificial way, dividing a very complex problem into a number of sub-problems that are all interconnected, interrelated. Now, and I'm not saying that it may not be a valuable exercise to do some of that, but I think we need to, as a community, have an understanding of the fact that we're never going to be like the computer vision community, because what we're dealing with is systems that are fundamentally, complex and interconnected with one another. And we have every decision that we make architecturally and in terms of how to divide the problem into sub-problems is a decision that has a lot of implications on how we address the global, more complex problem. Anybody else?
All right, anyone wants to add, or should we take the next question? Navid, you had one?
So thanks for the panel. So I've heard a lot of words that every one of you said, and I wrote them down. So we have data, we have AI, we have edge, digital twin, NTN, and I think the scope of 6G is very large, right? So that is what essentially each of you trying to say. And I think, Doug, you pointed out that we need to grow, OAI needs to grow. And I think things probably goes beyond just Eurocom and OAI. We truly need an ecosystem. Right. I think if really we want to go towards 6G, right, it will never be just Eurocom or OAI that takes the flag and go forward. How to deal with this diversity of all the players? Actually, in this panel, we already have a good sample, right? How do we do this? How this needs to be done?
Excellent question. Who wants to go first? Doug, Raymond, or Tommaso?
I don't think we know. I think you've clarified it better than I did, that OAI and Eurocom can't do it on their own. And so it's going to have to be a organizational structure issue with a lot of partners. And we're also going to have to look to how the world solves scalability issues in open source. I mean, we're not going to become Linux, right? It's not going to be a Linux size, but it's probably more like at least Kubernetes in size, right? And so we have to look at what happened with a project like Kubernetes. Kubernetes reached a point where it had to transition from one company or a small number of companies driving a code base into a massive community that has huge conferences and events, right, and things like that. Instead of 100 people, which is just unbelievably fantastic for OAI, you'll have thousands of people potentially who have a stake and an interest in this thing in a few years. And so therefore, you need to go to a whole nother, the reality is, the sad reality that none of us want to deal with is we have to go to a whole nother funding level. And we need to come up with a sustainable funding level that can support staff, including non-technical staff, just to manage relationships and to coordinate things, along with bringing in a lot of technical resources who can do the coordination of the architecture with all of these other groups and projects and integration. And that's why we've been trying to grow to hook up with ORAN Software Community and the ORAN Alliance, building a connection to AI RAN, which will happen for sure. And also, we need to deepen our relationship with 3GPP and ETSI and those organizations as well. You know, the answer is we need to grow up, and we need to grow in a lot of dimensions, and we need to do it fast, or we'll miss the ship, or we'll begin to look like we're not up to the task, and people will start going to other options.
Raymond?
Maybe this one works. I don't want anybody to take this in the wrong way, but we have a tremendous support from all of the companies behind OAI, financial support. In some cases, a certain degree of actual significant contributions in the code base. Now, again, going back to what Florian said at the very beginning, with being on time for 6G. The one, for me, key ingredient that's missing would be very significant contributions in the code base in the 3GPP components.
Yes.
That's very difficult, of course. I mean, that we can't obviously not expect the 3GPP partners to actually step in and go do that part, because that's the key business. But maybe a little bit more in terms of the following what the community is actually doing in that component, and maybe to get it going in the direction that would best serve the overall ecosystem. and I don't know how to do this. I mean, in the past, there were very many significant 3GPP contributions from Fujitsu, which was not one of the main 3GPP players. And that actually helped quite a bit. I mean, it was very difficult interacting with them because of the time zone differences and cultural differences. But I mean, that was very significant for us because it was really one of the first times we had that kind of a point-to-point contribution with a key player in the industry on the core software itself. So that for me is also an additional challenge that we can strive for with our partners to see how we can make that happen maybe a little bit better than in the past.
Okay. One last question. Okay, then we need to stop. I was just told.
Final one. Yeah, a bit more on technical requirements, if it's possible. It's related to SDR technology for 6G. What? Ah, yeah, of course. I did that before. Stefan already from Open Radio Systems, small startup from Germany. We are building basically hardware accelerators for ORAN systems. And my question is related to high performance computing, basically for SDRs. So we see this trend of softwareization, software-defined radios pushing open source, basically. And at the core of softwareization, there are basically general purpose processing, CPUs, for instance. And my question is, what requirements do you see, do we need for 6G and for building 6G SDRs on the CPU, on the high performance computing front? So current AMD EPIC CPU has 160 cores, 128 PCIe G5 lanes, right? With this, your frontal bus requirements are basically solved, more or less. At least with the 64 antennas. So what do you need on the high performance computing front in order to push SDRs for 6G forward? And maybe not just as a reference implementation, but maybe even in the field.
Okay. Anyone wants to take a stab at that? And NVIDIA has the computing.
Not NVIDIA.
Yeah, no, you
go ahead. But
you're not interested. You're not interested in GPUs.
In the real-time stuff, right?
I'm not sure if I'm the right person to respond to that. Just maybe make one point. You should you said it in the last sentence. You should distinguish between, let's say, prototype, test platforms, and what you actually enroll in the field. And I think when we talk about prototypes, then the requirements are maybe less strict and less. Also, the financial budget is maybe a bit higher. But I would hand it over to someone who can speak about it.
Maybe I can try and say. I mean, I think definitely the computing architectures that we have today are extremely powerful. But when it comes to doing 6G, some of that has to be on hardware accelerated platforms like the big matrix operations that are operating on 400 megahertz channels. That's not something you're going to be doing in software. I mean, that's just not going to happen. But in terms of the actual computing platforms, today we're quite agnostic. You mentioned AMD, so today we have solutions that work fine with the same piece of code on AMD, and it also works now on ARM. Maybe for 6G we have to get that working with RISC-V. Okay, but today RISC-V platforms are not there, really, to the extent where we could run something like OAI on it. But that kind of thing might be interesting in some of the parallel projects, working with communities like a RISC-V community to put out equivalent silicon with hardware accelerators, where we can use exactly the same implementation on something that might be more targeted toward an end product. And otherwise, I think we have what we need today. I mean, as long as we try and make the code base as agnostic as possible. So even to make it work with GPU acceleration, I mean, that's what we're doing now, and we're trying to do that more and more. And I think that's the key thing, to make the tools agnostic as possible with respect to the implementation technology.
All right.
Thank you very much.
I think we should close the panel. Maybe Doug, you wanted to say one last word to the previous question? No? Did I misunderstand you? Okay, sorry. Or maybe Tommaso, one closing statement?
I just wanted to echo your comments on, I think it's time for this community should position itself and get a posture of being an adult community, right? And go out there and say, there's commercial aspirations, right? In the sense that doesn't mean necessarily that the OAI code needs to go into specific commercial products, but it needs to create an ecosystem where there's products that will be built on top of that, and be the major player in this space. And I think we need, it's great to think of this as an ecosystem where we all benefit from this.
Thank you, Tommaso. That's a beautiful words to close the panel. Alain, you wanted to add something to that?
I would just actually say that we should make sure that we don't get into a teenager crisis. That's quite important. And we should also actually, we all discussed, the ecosystem is getting bigger, it's getting more complex. So we need actually also to weigh up our options. Where should we position ourselves? What we would like to focus on, so that we don't actually get overwhelmed into the so many things that can be done.
Okay.
Yeah. So I would just leave it with this.
Okay. So thank you. Yes, that was actually perfect words to close the panel, and that's exactly what these workshops are there for, to discuss all of this. So I invite you to do that. We have demos now. Some people left already on the lab tour. Well, let's first give a hand to the panel. Any organizational remarks? Coffee break and demos, and then social event, right? Social event is here. Yes. Okay. Thank you.
You just travel inside, then I know how much you